Hi students, so in this lecture we're going to talk about Faraday's law, and Faraday's law in general is just continuity for the Lenz's law. When you're talking about the Lenz's law, we end up to find the direction of induced current based on the change of the flux. So should we have the flux change and that generate a magnetic field to even cancel or reduce the magnetic field or flux, sorry. And the in Faraday's law, it's big, when in Lenz's law, we don't talk about any magnitude, talking about the directions. And here's the Faraday laws, which is the last piece to finish the formula for the electricity in the circuit. We're gonna talk about the amplitude, which talk of the induced EMF, which basically this is we have the current and we can calculate the current based to calculate the EMF, or we call it induced EMF. And the stated here for the Faraday's law, the magnitude of the induced EMF in the loop is equal the rate of the magnetic flux, or delta phi divided by delta t. Let's see here some example. Let's start with the first example. We have magnetic field going to the right, pass through the circular loop. It has a radius 7 centimeters, and the magnetic field so increase from 0.5 Tesla to 2.5 Tesla in 0.25 seconds. And that's good for the average of EMF, or the induced EMF. So before we start to calculate that one, we're gonna start with the Lenz's law. So Lenz's law, we're gonna see, since the magnetic field increase, so the according for the Lenz's law, he's gonna be reduced that increase. Talking about the reduce, that means he's gonna be generate the induced magnetic field point in opposite of the original magnetic field. So that directions will be in that directions. Okay, so that's what we call it the B induced, or the magnetic field induced. So from the magnetic field, or the induced magnetic field, we can identify the direction of the current through that loop using the right-hand loop. So we find it this one point to the side and point out of the side. That's the induced current. Now we can calculate our flux in both situations. In the situations we only have 0.5, and the situations we have 2.5. So we're gonna go back, quick reminder for the formula. Here is the phi I, of the initial flux, which basically is pi times r squared, is the area, times bi, which in this case, it is the magnetic field at the initial position. So we call it pi. We have the information that we need. We have pi times r squared, 0.07 meter squared, times the initial magnetic field, 0.5 Tesla. And that's calculations end up with the 7.7 power of -3. Don't forget the unit is Weber. Now, similarly, we can find the final flux, which the same formula, pi times r times final here, not the initial. And we have the pi times 0.07 to square and times 2.5 Tesla. And this number here will be 3.8 power to the -3 Weber as well. So it is -2. Okay. Now we can calculate delta phi, the change in the phi. So delta phi is basically phi final, or the flux final, subtract from phi initial. And this number here, it will be 3.1 power to the -2 Weber. So So now I have delta phi, so I can find the induced EMF. Induced EMF, absolute value, delta phi divided by delta t. Delta phi, 3.1 power to the minus 2 Weber, divided by delta t in 0.25 seconds. And in this number here, 0.12 volt. It's Weber divided by second, it is volt. So now we find the magnetic field. Now if we have electric circuit, that's the EMF what we can find. From there, we can find the current. So this is the basic energy or the basic EMF to apply for the circuit. So let's move to the second example here. And this example here, we given similar situations, but the only thing here is the magnetic field decreases, not increase. So the magnetic field not decrease, and they give you the rate of the 0.25 Tesla per second. That's what we are given. So basically what that means, the rate here, it is mean the change in the magnetic field or the rate of magnetic field is that one here it is 2.5 Tesla per second. So we are given this rate. Now, how I can deal with that situations? I am looking for delta phi to calculate the induced EMF. So basically, I can start from this definitions here from delta phi. Here is delta phi divided by delta t. That's the EMF that I'm looking for. So I am go from there. What I have the first one is the current. The area times final magnetic field. Area times magnetic field initial. Divide, I will keep delta t as it is. So from here, I can take the A as a common factor. So it will be A outside. Here is the A. A is the times what we end up with the B final minus B initial divided by delta t, which this one is the equal the area divided or multiplied by delta B divided by delta t. So I have this quantity. I need to multiply by the area. So here, the area we have the same area. Sorry, by times r squared 0.07 meter square and times 2.5 Tesla per second divided by delta t. We are given, we have this one so this one just multiplied by this rate, so times this rate. So calculation this one will be end up with 3.8 power to the minus 3 as the unit will be volt. It's very small value. So what I did just to play with my equation to end up with the rewrite my EMF as a function with the change in magnetic field. So let's see another example. And this example, we have the magnetic field as with magnitude 2 Tesla point to the right, pass through the circular loop with the radius 7 centimeters. And then what happened, the loop would change the directions in 40 degrees in 0.75 seconds. I have delta t here. What the average of the EMF generated by the loop. So here's what do we have in that case. So we're looking for the delta or the phi I and phi initial. So we need to find the phi I in the first part and the phi final in the second part. Then we subtract it to find our induced magnetic field. And similarly, so when we move that case, you already find the direction for induced magnetic field. And here, when you rotate your road or your circular, what happened for the magnetic field is going to be decreased, because if you flip it as the horizontal part, will end up with the 0. So the maximum value when he's perpendicular. When you turn by the angle, the magnetic field will be decreased. Decreased magnetic field means, according for the Lenz's law, it should be generate a magnetic field so to support or to increase the magnetic field by generating the induced magnetic field with the directions the same direction of magnetic field origin. The reason why, because the magnetic field will be decreased. That's the B induced in both cases, generating its own induced magnetic field that to support or to produce or to add more magnetic or induced magnetic field for that case. Now, according for right-hand rules, to find the magnetic field or the current, induced current directions. So just right-hand rules, you end up with this one comes in and comes out from this side. This is my induced current. Okay. So now what we're gonna do, we're gonna find our phi, initial phi. Okay, initial phi, we're talking about this case. So here is the phi initial. It will be by r squared times bi cosine alpha. What cosine alpha is, in this case here, the angle. It is 0 angle between the center and the magnetic field. This is the center. So we have here is the alpha equals 0. So we have here cosine 0. Okay. So in that case, I have pi times r 0.07 meter squared times magnetic field, in that case 2 Tesla. Cosine 0 will be 1. So we end up with this number here, 3.1 power to the minus 2. 3.1 power to the minus 2 Weber. Power to Weber. Similarly, we're gonna go to the final. By times r squared times b final times cosine alpha. What the cosine alpha is? The angle between the center of the rod and the magnetic field. So this is the angle, which basically right now, that's the angle what we are given, 40 degrees. So this one is going to be 40 degrees. Calculate this number with the numerical value that you have. You end up with the 2.4 power to the minus 2. 2.4 power to the minus 2. Again, Weber. Now we find both of the phi or the flux. Now I can find my induced magnetic or the induced EMF. Here is the delta phi divided by delta t. And here is we have phi final minus phi initial divided by delta t. And if you put this number here, you end up with the 9.6 power to the minus 3, again, volt. Okay, so that's the solution for this kind of, you apply the Faraday's law and to find the EMF or the induced EMF. Now let's see an example to how to deal with the EMF as the magnitude. We can deal it as the electric circuit. Let's see an example here when we have the rail and there's the rod is moving in that rail. We have two situations here. It's the part slide in 0 distance, and what the magnetic field, it's 0.1 Tesla. The bar pull out, moving to the right side, or to the left side, and make a change in that moving. It's just 0.25 seconds, just delta t in that case. So that's what the EMF generates in the loop and what the direction and magnitude of induced current. as we mentioned, talking about the Lenz's law, we identify the directions. Now from the Faraday's law, we can find the induced EMF, and then I can calculate as a magnitude for the induced current. So here, let's go to the first case. When I pull out the rod in the left side, what happened here? The flux will be increased according for the Lenz's law. It should be generate the induced magnetic field, resist that change. So we're gonna be generate induced magnetic field, and this magnetic field pointed to the bay. Here is the B induced in that case. So if I identify the direction of the induced current, right hand, my magnetic field point toward the page. So you will find magnetic field or the current induced current will be point in this directions, which basically clockwise. Now to find our EMF or the induced EMF, we're looking for delta phi, which is basically phi final minus phi I. Which is basically A is perpendicular to the final in both cases equals 0 times B final minus A. You can show this one A initial, A final minus A initial times B initial. So let's see, for the final here, I have rectangulars here will be 0.2 meters times 0.35 times the magnetic field in that case will be 0.1 Tesla minus AI I have here is the 0.2, sorry, 0.2 meter times 0.2 meters. So I'm talking about this is area. 0.2 meters times the magnetic field will be 0.1 Tesla. And this delta phi calculated will be end up with the 3 power to the minus 3 Weber. Power to the minus 3 Weber. Now, once I find the delta phi, now I can calculate my EMF based on the magnitude value of delta phi divided by delta t. So I have all the information that I need. Here is the 3.0 power to the minus 3 Weber divided by 0.25 second. And this is the induced magnetic field in that case, 12 millivolts. This is the first one. The second request asks to calculate the induced magnetic induced current. So I have the current goes here. So basically from the Faraday's law, we identified our EMF. So if that current goes to the true resistors, so I can find my I, just Ohm's law, in that case will be EMF or this EMF divided by R. So in this case, I have 0.012 volt divided by 1 ohms. And I end up with the 12 milliamp. That's how we use the Faraday's law with the Lenz's law to identify, calculate the direction and induced current and the magnitude of the induced current.